The existence and uniqueness theorem, like a lot of theorems in math, starts with an if-then statement. If certain conditions are true, then we can guarantee certain conclusions must also be true. The then part is really all about existence and uniqueness. Essentially, if we have a certain initial value problem, the then part is then we can guarantee there is a solution and also only one solution. Then the initial value problem has one and only one solution. And the one and only one is really what existence and uniqueness is all about. Existence, if we say a solution exists, we're saying there's at least one solution. If we say the solution is unique, we're saying that's the only solution. There's not more than one solution. And in a lot of ways, this is very similar to the idea of knowing a line, a linear function, based on the slope and one point. Like if I say we want, if we just have like a standard XY axis, if I say we want a line with slope -1/2, how many solutions are there to that description? How many functions are there that are aligned with slope -1/2?
A lot.
A lot. Specifically, how many a lot?
Infinite.
Yeah, there's infinitely many lines with slope -1/2. These are a few of them. So there's infinitely many lines that fit this description. A solution to this description exists, but it is not unique. But what other information will we need to narrow it down to just one solution, just one function? Slope -1/2 and what other information?
An initial condition.
Yeah, we'd need an initial condition, which in this context would take the form of some point that it passes through. Probably the y-intercept, but it could really be any point that it passes through. So let's say, and passing through, let's say the location 1, 5, 1, 5, so something like this. There's only one line that has slope -1/2 and passes through the point 1, 5. Knowing the slope of a line is like knowing a differential equation. There are infinitely many lines with a certain given slope, and likewise, there are infinitely many solutions to a differential equation because the differential equation tells you something about the slope of a curve. But if we also have an initial condition, that narrows it down to just one solution. There's only one line that has this slope and passes through this point. So that's the sort of thing the existence and uniqueness theorem is talking about. Given a certain initial value problem, like knowing something about the slope and knowing a point that it passes through, we want to be able to narrow it down to, first of all, guaranteeing that there is a solution and that that's the only solution to the differential equation that passes through that point. For a line, that's pretty straightforward. If you know the slope and one point, you can show that that's the only line that matches those conditions. For a differential equation, we need a little more detail, a little more complication. So the initial value problem itself takes the form of a differential equation. Let's say y prime equals, could be something about y and possibly t as well. Let's say that's f of t and y. So just some function of t and y. Y prime equals something about t and y that we're calling f, a function for now. And also we need initial conditions. Let's say the initial conditions t equals t naught, y equals y naught. So some initial t value, initial y value, a point that the curve has to go through. That's an initial value problem. We want to know what conditions have to be true. What's the if part? So we can guarantee that this initial value problem has one and only one solution. So what do you think has to be true there? What has to be true about this differential equation so that we can guarantee there's one and only one solution?
We just said that it has to be continuous on f and the partial f or partial y.
Yeah, the function itself has to be continuous because if you have any discontinuities, then that means there's some ty coordinates where the derivative doesn't exist, or where it's a perfectly vertical line, which means it's not really a function. So we need this function to be continuous. If the function f of ty is continuous, and it doesn't have to necessarily be continuous everywhere, it just has to be continuous on some region. Let's say some region R of the ty plane. So maybe it's not continuous everywhere, but we can narrow it down to a certain region where everywhere on that region it is continuous. And of course, in order to be meaningful for this problem, that region would have to include what point?
Wait, sorry.
What's the one point that has to be in that region in order for this problem to make any sense?
The initial condition?
Yeah, the initial conditions has to be on that region of continuity. The point t0, y0. So having the function itself, the y prime equals whatever, having that be continuous, it turns out that only guarantees that there is a solution. It doesn't on its own guarantee uniqueness. To guarantee uniqueness, we also need one other condition: the partial derivative of that function with respect to y. And the reason for that ultimately has to do with a certain approximation method. There's an approximation method you can use to make a guess for the solution and then refine it to be a better guess and a better guess and a better guess, continue repeating the process, and you approach the actual solution. But it turns out that only converges to an actual solution if this partial derivative is also continuous. So we need the function that's equal to y prime and its partial derivative with y. We need those to both be continuous. Again, not everywhere, but just on some region, usually a rectangle, but I don't think it has to be a rectangle. If I remember correctly, the function itself being continuous guarantees there is a solution. This partial derivative also being continuous guarantees that that solution is unique. So that's the existence and uniqueness theorem for any first order differential equation. As long as you can write it as y prime equals something about just t and y, we can say that if the function that's equal to y prime and its partial derivative with respect to y are both continuous on some region that includes the initial conditions, then that initial value problem has one and only one solution on that region R. Outside of that region of continuity, we can't necessarily guarantee anything. Maybe it has a solution, maybe it has many solutions, maybe it has no solution. But on that region, we can guarantee a solution and only one solution. Any questions on that so far?
How does this play into like part of the theorem of y equals phi t and like t0 minus h less than t0 plus h?
Which one is that?
That was part of the theorem. That like
that's the yeah, that's the interval we're talking about.
Yeah.
I was just describing it as some region R, but it looks like the way the theorem is formatted in the textbook describes it as a rectangle. That if you've got t0 and y0, any rectangle that includes that point can be bounded by y values a certain amount above y0 and a certain amount below y0, and t values a certain amount to the left of t0 and a certain amount to the right of t0. So I think that's what the textbook is describing there. That we're talking about yeah, y value or t values from alpha to beta, and y values from what, lambda to delta. So the book is just describing variables representing the bounds of that rectangle. That as long as we can establish some rectangle, including the initial conditions, where the function is continuous and where the partial derivative is also continuous, then we can guarantee that within that rectangle, we can guarantee a solution and only one solution. That we might not know what that solution is, but we can at least say there is a solution that exists within that rectangle. Any other questions on that so far? Then let's try out a quick example. Yeah, let's try that one out. Let's say we have this differential equation, y prime equal, or y prime times y minus 4 equals x squared plus 2x. Does that look like it has any discontinuities?
No.
Not on its own. But the thing is, this needs to be written. In order to apply the theorem, we need to write the differential equation in exactly the format the theorem describes. So if we want to rewrite this as y prime equals f of ty, what would that f of ty have to equal?
X squared plus 2x over y minus 4. And there'd be a discontinuity at 4.
Exactly. So when we write it in this exact format, which is necessary to follow the theorem, this function right here is what we call f of, I guess this would be f of xy. And that does have a discontinuity when y is 4. So that suggests that there is some problem going on at y equals 4. And if we take the partial derivative, what's going to happen when we take the partial derivative with respect to y of this function?
It'd be x squared plus 2x times ln, wait, ln y minus 4?
The derivative, not the integral. It might help
Oh.
you think of this as a quotient rule sort of thing, that we've got a function over a function.
Yeah.
The top function is a constant, though. So
Mhm.
we could think of that as just, if we have f equals just a constant times y minus 4 to the negative 1. What's the derivative of y minus 4 to the negative 1?
Just 1. I mean, wait.
With respect to y. What if the minus 4 wasn't there? If it was just y to the negative 1, what would be the derivative?
ln 4. Wait, no.
Integral.
Negative 1 over 2 y.
Negative 1 over, and we so
Oh.
we multiply by the original exponent, and then we can just
Oh, y minus, or over y minus 4 2 or squared.
And then chain rule would say multiply by the derivative of what's inside, but that's just 1. And then we also still have the x squared plus 2x in the numerator. So that's the partial of f with respect to y. Does that introduce any new discontinuities that we didn't already have?
No.
So it looks like we still just have y can't be 4.
Yeah.
Sometimes the partial derivative does introduce new discontinuities, so you do need to check. In many cases, it just repeats the same discontinuity you already have.
Mhm.
So it looks like y equals 4 is the only discontinuity. If we try representing that on a graph, let's say we have our x versus y graph. If we were to graph the discontinuity y equals 4, y equals 4 is just going to be a horizontal line at height 4. That splits the plane into how many regions?
2.
Yeah, 2 regions. So that suggests 2 regions where the function could exist. Either the function can be guaranteed to exist above 4, but can't be guaranteed anything about crossing the line, or it could be guaranteed to exist below 4. And how would we choose which one?
The initial condition.
Yeah. So for instance, if the initial condition was like 1, 1, then we could say we can guarantee that there is a solution and only one solution to the initial value problem. But we can only guarantee that on the region below y equals 4. We can't guarantee anything beyond that. That probably means that the solution is going to approach y equals 4 as an asymptote in one direction or the other. It doesn't necessarily guarantee it, but that's probably what's going to happen. Or likewise, if the initial condition was like 1, 5, then we can guarantee there's a solution above y equals 4, but we couldn't guarantee anything beyond that. Or as a third possibility, what would happen if the initial condition is 1, 4? What would that tell us?
And it doesn't exist.
It might exist. We just can't guarantee that it exists. Because note that the existence and uniqueness theorem says if all this stuff is true, then we can guarantee a unique solution. It does not say anything about what happens if this stuff is not true. If this is not true, then we just can't conclude anything. Maybe there's a solution, maybe it's unique, maybe it's not unique, maybe there's no solution. So if the if part is not true, then you can't say anything about the then part one way or the other. We would just say we can't tell anything about this from the existence and uniqueness theorem.
Okay.
But if the if part is true, then the then part must be true.
Yeah, and then
Mhm.
when we write out the answer, it has to be in like some formulaic way.
The problem with the existence and uniqueness theorem is that it's really difficult to write actual homework questions or test questions that really check, do you genuinely understand this? So usually the test questions and homework questions I see about this are things like, here's a differential equation, find what interval you can guarantee it exists on. And
Yeah,
so for
so
stuff
for-
like that, you would just say, like, let's say the initial condition was below 4, let's say 1, 0. In that case, you would say we can guarantee that there exists a unique solution on the interval or on the range x goes from -infinity to infinity, y goes from -infinity to +4. So we
Got it.
typically write that in interval notation,
Okay.
focusing mainly on the discontinuities. Any other
Okay.
questions on that so far? And if we do consider specifically a linear differential equation, then this theorem becomes much simpler. If we're talking about a linear differential equation, that's going to be of the form specifically linear first order. If it's linear in first order, that guarantees we can write it as y prime equals, what would this f of ty have to look like? What does it mean for a differential equation to be linear?
There's no like quadratic functions or exponential.
So for instance, would this be linear?
No,
Because
it's trig. Because
Right.
it's not, it oscillates. It's not a straight line.
well, the thing is, linear differential equations don't have to have straight lines as solutions. In fact, they don't even have to have solely linear functions. For instance, this is a linear differential equation. Because even though we've got weird functions going on, what's not happening?
I don't know.
Where does y show up in this differential equation? Do you remember the idea of linear combinations from 22A, linear algebra?
Not really.
the whole idea of linear differential equations, in fact, a lot of the situations where we even use the word linear in higher math is really all about linear combinations. If you have, for example, let me clear some more space here. If you have some vectors, a collection of several vectors, let's say v1, v2, and v3. How could you combine those vectors? What could you do with those vectors in a way that we would call a linear combination?
Add them or subtract.
You can add or subtract. And also, what could you do to each one before you add them up? Yeah, you could rescale them with a scalar multiplier. Let's say C1, C2, C3. So a scalar, just an ordinary real number, times the first vector, plus another real number times the second vector, plus another real number times the third vector. And these don't even have to be constants. They just have to be scalars rather than vectors. So this would be called a linear combination of those three vectors. And when we say linear, we're really talking about combining these things by just multiplying them by scalars and adding them together. And the reason we call that linear is that if you are talking about, like, let's say you have just multiples of one vector, that's going to form a straight line in the direction of that vector through the origin. Linear combinations of two vectors are going to form a plane through the origin. So it's flat. It's still linear in the sense of not curving at all. And then at a third one, we get a three-dimensional space, but it's still going to be a non-curved three-dimensional space. It's still going to be linear in that sense. So we use the word linear to describe linear combinations like this. If we translate this into the idea of differential equations, a first order equation could have a y prime term and a y term. A linear combination of those would mean you're multiplying each one by some scalar, which in this case, again, doesn't have to be a constant. It could be any function of t. So let's say a of t times y prime plus b of t times y. And that could add up to some other function of t, let's say c of t. So this is what we mean by a linear differential equation, not just that certain types of functions don't happen in it, but specifically that it can be written as something y prime plus something y equals something. And for second order, you could have also a plus something y double prime term. For third order, you'd have plus something y triple prime and so on. The important thing is that all we're doing to y and its derivatives is linear combinations. Each one is multiplied by something, which might be a constant or might be a function of t, and then added together. So that's what we mean by a linear differential equation, linear combinations of y and its derivatives. Any questions on that so far?
No, I think I got it.
So for first order, we just have something y prime plus something y equals something, if it is a linear first order. But we wanted, for the purposes of the existence and uniqueness theorem, we want to put it in this format, y prime equals something about t and y. So we'd want to isolate y prime here. If you isolate y prime, what would you get?
Minus bty plus ct all over at.
Yeah, and we could split that up, just have each one divided by a of t. But the thing is, a, b, and c are just arbitrary functions of t. So if you divide two functions of t, you just get some other function of t. So let's just call this, let's say, g of t. And let's call this other one, the c over a. Let's just call that maybe, let's say, h of t. So we now have y prime equals a function of t and y. So this is our modified, simplified f of ty for linear differential equations specifically. Any first order linear equation can be written as y prime equals something about t times y plus something else about t. And those functions could be constants, they might even be zero, but they could be any function of t as well. And if we try applying the existence and uniqueness theorem to this specialized case of linear first order differential equations, we can say we need f of ty, that is this whole thing, to be continuous. So for continuity, is there any possibility that a t value might make this discontinuous?
If the whole denominator equals 0.
Well, we don't have any denominators here. It's just g of t times y plus h
Oh,
of t.
sorry, yeah. Then no.
So there's no way that any t value could make an arbitrary function of t discontinuous?
No.
What if that arbitrary function is, for instance, logarithm of t?
Oh, then I guess.
Right, it depends on what those functions are, right? Like if this is just some function and we don't know anything about it, we can't say whether it has any discontinuities or not. Any function of t might have some discontinuities. So we would need to check, does this have any t values that make it discontinuous? And also, does this have any t values that make it discontinuous? But what about y values? Are there any y values that would make this whole thing discontinuous?
No.
Right, you can plug in any y value you want here, right? If we just have something times y plus something, this doesn't provide any restrictions to what y can be. Y could be anything. So that means if we rethink the if part, if we think of f of ty as this whole thing, this is never going to have any y values that lead to impossibilities. There's no y values that cause problems here. So we don't even need to worry about a region in terms of t values and y values. We just need to worry about an interval of t values and check, do the t values lead to g or h having any discontinuities? So instead of f of t and y, let's just look at g of t and h of t. And that way we don't need to look at some rectangular region because we don't care about y values at all. There are no y values that can possibly cause any problems here. Every y value works fine. Instead, we just look at t values. So instead of a region, we can say an interval of t values. And then we don't really need to worry about why not. We can just say an interval of t values that includes the initial condition t naught. So an interval of t values of the t-axis. And then if we take the partial derivative, what would be the partial derivative of this whole thing with respect to y?
G of t.
Yeah, because we're treating anything involving not y as a constant. So we just get, if we just got a constant times y plus a constant, the derivative is just that constant. And that doesn't introduce any new discontinuities. So we don't need to worry about the partial derivative at all. The simplified version of existence and uniqueness theorem for linear differential equations, if you've got it in the form of y prime equals g of t times y plus h of t, all you need to check is those functions of t, see if those have any discontinuities for problematic t values, and then chart that out on a number line. For example, if your differential equation is something like, let's say y prime equals 1 over t plus 3 squared times y minus logarithm of t minus 5. Does this have any discontinuities?
Yes.
And what would those be? T cannot equal
-3
-3
and 5.
and 5. And moreover, you can't take the logarithm of a negative number.
Yeah.
So that says not only that t can't be 5, but that t has to be what sort of value?
Greater than 5.
Yeah. So we could put this on a number line. Our only restrictions are t cannot be -3. And t must be greater than or equal to 5. Or not even equal to, just greater than 5, not including 5. So it looks like we only really have one interval that we need to care about. We don't even need to worry about the -3 because that doesn't make the greater than 5 true. So in this case, we would say that the interval of continuity is t must be on the range from 5 to positive infinity. We don't need to worry about y values at all because there are no y values that make this discontinuous. We just need to say, as long as the initial condition has a t value that's greater than 5, then this works. We can guarantee a solution and only one solution on the interval from t equals greater than 5 to infinity. As long as t is greater than 5, we're fine. So that allows us to use the simplified version of the existence-uniqueness theorem because this is a linear differential equation. And in general, differential equations tend to be easier to analyze, easier to solve, easier to graph if the differential equation itself is linear. In fact, a lot of situations involving nonlinear differential equations, if it can't be solved directly, usually what we do is create a new linear differential equation that's at least close to it, a linear approximation, and then solve that instead to get a close enough approximation. Any other questions on that theorem so far?
I think I'm all good. Thank you. Thank you for the explanation.
Yeah, you're welcome. And let's take a look at this sample problem that was requested also. Problem 8 from homework number 2, where we have an initial value problem. Copy that to the board. So y prime equals 2 times cosine of 2x over 3 plus 2y. And we're also given the initial condition, y of 0 equals 1. That is when t is 0 or negative 1. When t is 0, y is negative 1. And we could start this by checking the existence and uniqueness theorem. Are there any x or y values that would lead to discontinuities here? Yeah, y can't be, or I guess that'd be negative 3 halves, right? Because if y is negative 3 halves, this becomes negative 3 plus 3, which cancels out. So we know we can't have y being negative 3 halves. And I think that's the only one. There are no x values that cause problems for cosine. You can take the cosine of anything. If we take the partial derivative with respect to y, we're just going to get a 3 plus 2y squared in the denominator. So that doesn't introduce any new discontinuities. So if we made a graph of this, the only problem is that y equals negative 3 halves. We've got a discontinuity there. So we can expect that the solution will exist above that discontinuity or below that discontinuity. But we can't say anything about crossing that discontinuity. With that in mind, let's try solving this differential equation. Based on the structure of the differential equation, what technique do you think would work well for solving this one? Yeah, separation of variables, because we have, if we write this as dy dx, this is just a function of x and a function of y combined with multiplication or division. In general, anytime you've got a function of just x and a function of just y combined with multiplication or division, that works really well with separation of variables. We can just multiply both sides by dx. And divide both sides by, actually, I guess we want to multiply both sides by 3 plus 2y also. That gives us 3 plus 2y dy equals 2 cosine 2x dx. And this 2 could go on either side of the equation. You could also divide by 2 if you want. Constant multipliers can go anywhere, but we may as well just leave that there. And then what's our next step? Now that we've separated the variables.
Integrate.
Yeah. Apply an integral sign to both sides. 3 plus 2y becomes what? 3y plus y squared equals, and then what's the integral of 2 cosine 2x?
Sine of 2x? Well, because of the 2 in front.
Right. Yeah, because the derivative of sine of 2x would be 2 cosine 2x from the chain rule. And we've got this 2 here, so that takes care of that. You could also do that in a few more steps with the u substitution if you like. And since we're looking for, at the moment, we're looking for all possible solutions, we also need to include a plus a constant. Any questions on that so far? And ideally, we'd like to be able to write this in explicit form. We want y equals some function of x. That is, we want to isolate y on one side of the equation. Problem is, we've got a y squared and a y term. So how could we solve this for y?
The square thingy.
Yeah, one way would be to complete the square, turn it into a perfect square quadratic, and then take the square root. So we could do that. We could say, what would we have to add here to make this into a perfect square quadratic? Yeah, if we add, because if we take this 3, divide by 2, and then square it, 3 over 2, and then square it. So that's 9/4. So that way, this is 2 times 1.5. This is 1.5 squared. That means we can now factor this. And that should be y plus 3/2 squared. So you can always use completing the square. Figure out what you have to add to turn this into y plus or minus something squared. And then on the other side, we've got sine of 2x. And also we've got an arbitrary constant plus 9/4. So what's that?
You just make it c.
Yeah, that's just some other arbitrary constant c. The plus 9/4 can be absorbed into the constant we don't know anyway. At that point, we can now take the square root. But since we're taking the square root of both sides, what do we need to include?
You mean plus or minus?
Yeah, because it could be positive square root of all that stuff, or it could be negative square root of all that stuff. In the same way that, for instance, if you know that a squared equals 9, a could be positive 3 or negative 3. Subtract 3/2, and we now have a formula for y. So this is our general solution. It contains infinitely many possible solutions because c could be anything, and we could have plus or minus here. So how do we narrow it down to one specific solution?
You'd use your initial condition, right?
Yeah, go back to the initial condition. The information about the slope tells us a whole family of solutions. Knowing a point that it goes through narrows it down to 1. And that point, -1, is not on the discontinuity. It's above the discontinuity, so we should be fine. If we actually fill that in, we could say, replace y with -1 and replace x with 0. So we fill in -1 for y, -3/2 plus or minus square root of, and then sine of 0 is just 0. So we just get 0 plus c. And then we could solve that for c. First of all, though, we've got a plus or minus here. If you're at -3/2, would you have to add or subtract in order to get to -1?
Add.
Yeah, -1 is greater than -3/2. -3/2 is down here, -1 is higher up. So we're going to have to add, not subtract. And that tells us which sign to use here. So the initial conditions allow you to solve for c and also allow you to decide should you be using plus or minus, if there's a plus or minus sign. So we assume this is plus. To get rid of the -3/2, let's add 3/2 to both sides. -1 plus 1.5 is 1/2. Note that that's positive, which is another sign that this has to be positive. So 1/2 equals square root of c. So what does c have to be?
.25.
Yeah, square both sides would get a quarter. So that means for the specific solution, in order to pass through this point, c has to be 1/4. So we can now fill in, we now know this plus or minus has to be plus in order to hit that initial condition. Graphically, that's because we want to be -3/2 and up. If we'd use negative, we'd be using -3/2 and below. So -3/2 plus square root of sine of 2x plus 1/4. So that's going to be some sort of weird oscillator. What's that even going to look like? I guess it's also going to start at, it's going to be restricted in terms of x value, because if x is too small, we get, does that work? Yeah, I guess this is possibly going to lead to discontinuities if that leads to a negative result as well. Yeah, go ahead.
And we want to go up towards -1 only because that's our initial condition, right? If we were given like an initial condition of -2, we'd want the minus and go that direction.
If the initial condition had been below -3/2, this would have to be minus in order to get below that.
That's what I thought. I just want to make sure. Thank you.
This is also asking us to solve the problem numerically using a direction field. So if we draw this on a direction field, let me pull that up and we'll take a look at what that actually looks like. Direction field, there we go. So here's a direction field. Let me rewrite this as y prime equals, let's make it a function of x. Y prime equals 2 times cosine 2x divided by 3 plus 2y. And we'll graph that subject to, yeah, I think that'll be all right. Maybe we don't need as much x value, maybe up to, I don't know, 6 or something. So here's what the direction field looks like. And if we specifically want the solution with initial condition 0, -1, we can fill in 0, -1. And that's all we really get. Wait, that wasn't 0. Let me think that. 0 is here. So 0, -1. That's our initial condition. So this is what our graph looks like. If we had been below, we might have gotten, oh, I think it's running into problems with, yeah, when we get too close to the discontinuity, this runs into problems.
Usually,
yeah, go ahead.
Dr. Taft said to hit stop and then click it like when you click the initial value at 0, 1, it only does part of it, and then you just press stop on the
0,
on the top left. And
yes.
Yeah, and then it'll continue on the other side.
Okay, thank you. Yeah, I think the problem is as it gets closer and closer to the discontinuity, it gets locked in a loop of calculating more and more and more values, but never actually getting there. But it looks like this is what our solution curve will look like. And let's take a look at a few more. And notice that it has to stop as soon as it hits -1.5 because that's a discontinuity. But if we had used negative instead of positive, I think we'd get a solution like this. So if we include positive and negative, we'd get sort of a loop. And then we get some other interesting curves further up and further down. It just turns into this weird discontinuity when we get too close to -3/2. But this is what some of the other solutions would look like.
When I graphed it on a different website on GeoGebra, there were multiple humps, because when you just clicked 1, 1, 0 or 0, 1, 0, -1, it was just that one hump that was made.
Yeah.
But then in a different website, when I put in my particular solution, it made multiple at pi/4 plus pi n, at multiple.
Something like this.
Yeah.
I think the reason for that is that like this curve and this curve have the same function. They both be the same way of writing out the specific solution. But it's a multi-part function that is interrupted by the discontinuities. So if you're using a grapher program that graphs the function, then it would graph all of those humps. But this one's not actually graphing the solution itself in the sense of a function. Like notice that nowhere in here did I type in this function. And the program isn't explicitly solving the differential equation. The program doesn't go through these steps and find an explicit solution and graph it. The program just takes the point you click on and it thinks, well, from there, I've got to go this direction. So I'll go a little further there. And from there, I've got to go this direction. And from there, I've got to go this direction, which is why it seizes up like this when it hits a discontinuity. When it hits that discontinuity, it doesn't know which direction to go. So only that one hump is graphed because that's the only continuous region that includes that initial condition. So this program is actually obeying the existence and uniqueness theorem, not because it's been specifically programmed in, but because by following the direction field, when it hits a discontinuity, it doesn't know where to go from there. And that's where the existence and uniqueness theorem hits and says you can't go beyond that point. We can't guarantee a solution past that point.
So do you think for our homework, when we're graphing out the solution, would it just be one hump, that one hump? Or like
Yeah, I would say just that one, because that's all we can guarantee is part of the solution. That's the only part we can guarantee is part of the solution. I would say just graph the part on the interval of continuity that includes that initial condition.
Okay.
Any other questions on that?
Yeah, I did. So I didn't do the whole complete the square thing. And I just inputted my initial condition as it was in the implicit. I believe that's the implicit solution when you have y squared. And I got C is -2, but I got the exact same answer in the end. Is that?
Yeah, if you before adding 9/4, if you just plug in the initial conditions here, that will give you a C value that leads to the same solution.
Okay.
The only problem is if you plug in the initial conditions here, you don't know in advance whether it's going to be plus or minus. So you would just need to check again at the end.
Gotcha.
And by the way, another way to solve that, you could use completing the square, or you can move everything to one side and then apply the quadratic formula. Because the quadratic formula is basically just an automated version of completing the square anyway. It ultimately does the same thing. So whatever way makes the most sense. Any other quick questions on that? All right, then I will see you next time.
Thank you.
You're welcome.